Hello everyone, welcome to my today's presentation with the title Influence of the Composite Structural Parameters on the Mechanical Performance of Additively Manufactured Composite Metal Hybrid Materials. My name is Sergio Amancio. I'm at Graz University of Technology in Austria, and will present this paper on behalf of my PhD student, my past PhD student, Mr. Falck. The contents of this presentation, I will start with a short motivation and introduction of the so-called AddJoining process, describe the objectives and the methodology, and then go through some selected results, pointing out some highlights of the design of experiments and statistical analysis of this work, and then the joint optimization in terms of quasi-static, lap shear force, and a short comparison with reference joints that were produced with the aid of adhesive bonding. So, additive manufacturing of metal polymer hybrid structures is a very young knowledge area in additive manufacturing. And if you try to summarize the main steps, we can say that this is a multiple step manufacturing process which is composed by a first step. So the first step consists of the metal fabrication or preparation, for instance through subtractive or formative processes like milling, forming, cutting, and so on, or by additive manufacturing, including powder bed fusion, for instance, or all powder bed additive manufacturing process, as well as the directed energy deposition processes, followed by the metal hybridization by polymer or polymer and composite additive manufacturing, for instance by the use of fused filament fabrication, as we can see here in figure or step 2. For continuous fiber and reinforced polymers, nowadays there are only the possibility of using fused filament fabrication. Of course, the interface between the metal and the polymer will play a very important role, and the interface modification can be done basically through the current surface pre-treatments using adhesive bonding, or microstructuring through different processes using high energies such as laser or electron beam, so that you can have a better surface preparation and a better connection of the polymer to be deposited on the top of the metal. Of course, using of process optimization tools such as design of experiments and artificial intelligence are very important in order to support the process understanding and optimization, as well as the use of computational modeling and simulation tools to support the improvement of the mechanical resistance, for instance, or the microstructure, so that we can get to a hybrid structure, as you can see in this example, a metal stringer hybridized with continuous fiber reinforced polyamide 6. So the motivation is to achieve hybrid layered structures using unreinforced or fiber reinforced thermoplastics and lightweight metals to tailor material properties, for instance as to improve the strength to weight ratio in a vehicle or an airplane, to decrease emissions and fuel consumptions, for instance, to attain higher reproducibility through automation, as well as clean production routes in comparison to the state-of-the-art lamination composite processes. And the fact of working with thermoplastic-based materials, you can enable a better repairability and recycling. So we are supporting the circular economy by using additive manufacturing and combine those materials listed here in this slide. Without losing time, I would like to introduce you the AddJoining process, which is a patent application of Mr. Falck and I. So basically, in this patent, we use fusion filament deposition or fused filament fabrication, where we have the metal part in black placed in a building platform, which is heatable, so you can change the temperature. And we have a double extruded here, one with unreinforced filament and the other with reinforced filament here. So a double extruder head. So the first step is to deposit a so-called coating layer. So it's a very thin layer that has a similar function as an adhesive, but it's composed of the same composition of the fiber reinforced composite. And this is then placed on top of the metal, and then the process continues, alternating the deposition of fiber reinforced and unreinforced layers until you get an overlap joint or an overlap structure where you have a composite-like structure deposited in or on the top or around the metal part. So I would like to show a short movie showing the fabrication of the specimen I'm going to present. So what you see here is the last layer of continuous fiber reinforced polyamide 6 being deposited on a substrate of aluminum 2024, both materials used in aircraft. Examples of potential applications when using the AddJoining based FFF are in aircraft, which is the focus of my work. So different layer panels fabrications, also combining honeycomb structures, as well different primary structures where you have, for instance, reinforcements of polymer and composites on a structure of metals, such as skin stringer connections, or in the cargo floor beam, as we did in published this study here, where we can then connect and print directly the hybrid structure and connect that to the structure, the metallic structure of the airplane. So the objectives and methodology of this work is to evaluate the effects of the so-called composite structural parameters on the ultimate lap shear force of joints made between aluminum 2024 and polyamide 6 composite reinforced with carbon fiber in a form of overlap joints. And to compare the ultimate lap shear force of the AddJoining in comparison to adhesive bonding reference joints. For that, as I mentioned, we select aluminum 2024 2mm rolled sheets with this microstructure, as you can see here on the top. And we work with two filaments, one unreinforced polyamide 6 and the continuous fiber reinforced polyamide 6, as you can see here in the picture, a cross section of the part of the filament. Here are a few properties that you can read if you have interest on some physical, chemical properties and mechanical resistance of those base materials used here. In this work we use a MarkForged Mark II from the MarkForged company. This Mark II actually with a modification, so we modified and create a tailor-made heat system where we can fix the specimen and heat up the metal plate indirectly. So the AddJoining structural process were optimized and analyzed by design of experiments where we use a 3K full factorial, so 3 levels and 3 factors, so 3 AddJoining parameters, which were the number of CFPA6 layers, so the number of carbon reinforced layers, its distribution, and the orientation. Such as like this is schematically represented, we work with 4, 6, and 8 layers. We work then with a distribution, so-called alternate, mid-plane bottom and mid-plane top, which I will explain to you. So the alternate is like in a traditional composite laminate, and the middle plane bottom, we have all CFRP layers concentrated in the center of the thickness of the composite part in the hybrid joint. The mid-plane top, we have divided the amount of composite carbon reinforced layers on the top and on the bottom in the composite part. Then we tested traditional orientations, 0 degree, plus minus 45 and 90 degrees to the load orientation. And as an example here for the alternate, we have 16 layers where in this example we have 0 degrees in the carbon reinforced, plus minus 45 on the unreinforced, and so on and so forth. We use a coating temperature of 200 degrees and 29 and a heating bed temperature of 77 degrees Celsius. For the lap shear testing, we use, of course, the ultimate lap shear force as the answer being analyzed from the DOE, and we use an adapted specimen geometry from ASTM D3163-01, as you can see here in the description. So a single lap joint. Let's go for some selected results here. Starting with the DOE statistical analysis, we use analysis of variance to analyze the response ultimate lap shear force using alpha of 0.05, so a 90.5% of confidence on this analysis here. And this is the ANOVA table with different data here from the statistical analysis, like the mean square errors, some parameters F as the F value, but let's concentrate on the P value. So meaning if we set an alpha of 0.05, our P value should be equal to 0.05 or less if the factor, or in this case the process parameter, is relevant. So in this case, from this analysis, the distribution of fibers, the orientation of fibers, and the number of fibers were relevant, as marked in green here, and the two-way interaction between the distribution and the orientation was also relevant. So we could generate equations for predicting the ultimate lap shear force for the different dispositions of the composite. So for the alternate, for the mid-plane bottom and mid-plane top. So are the equations of the reduced models, meaning we remove the non-relevant factors for the model, and we made the regression, as you can see here. Before we go through the analysis and process optimization, of course, we validated the model by producing additional validation runs marked in dark here. As you can see, there is a very good fitting of the model. So the adjusted R2 is 81.4, and the predicted R2 is 75.7, meaning that the model is very good to fit the data. So pretty much good for fitting the data in the range of analyzed factors or analyzed adjoining parameters, and also has a fairly good prediction power of combination of process parameters that are outside of this range studied here. So all the influences of the single variables on the ultimate left shear force are available upon request. We publish that. We can send it to you if you have interest. So let's focus on the process optimization because of the time available. So what we have here are plots between the number of layers and the orientation of the layers. And we have here in different colors the ultimate left shear force for the alternate condition, for the middle plane top, and for the middle plane bottom conditions. And here are the results, so the cross-section overview in the overlap area or of the produced specimens for the alternate, for the middle plane top, so the carbon fiber here, carbon fiber there, and all carbon fibers in the middle, in the mid plane bottom specimens. And here are the results. So we select the specimens in the area resulting the highest resistance for all of them, and then these are the tests resulting different values of ultimate left shear force, whereby the alternate and the middle plane top are very similar, so statistically the same. So we proceeded further. With the analysis, and here, if we go for some detailed microstructure characterization, what you have here in white is the aluminum part. The aluminum part was sandblasted in advance to increase the roughness surface, and then here the different distribution of fibers. So there was a visual mechanical interlocking between the polyamide 6 coating and the aluminum. So if we draw imaginary line here, we have the coating layer, so the first unreinforced, and here the first, let's say, unreinforced layer from the composite part. As you can see, there is no visual gaps between the metal and the polymer in the coating layer, and there was a very good bond formation between the first unreinforced layer and the coating, so as you can see here. But in the case of the mid-plane bottom, we saw some delamination defects between the first layer, or within the first unreinforced layer, as you can see here, and this is being is still under investigation, but we believe that this is due to the differential thermal contraction between the unreinforced volume and the reinforced volume in the printed layers, which generate those residual stresses that led to the lamination cracks. So this explains the reduction of mechanical resistance. Therefore, we went to the alternate condition. So the alternate conditions has a very low standard deviation compared to the other ones, and this was then used for the comparison that will be shown in the next slide. So here we took the optimized condition and compared that with adhesively bonded joints. So the adhesively bonded joints were produced following aeronautic and aerospace procedures in the industry. Also, we use epoxy-based adhesive, which can be bought commercially, normally used in aircraft applications. And here are a cross-section showing the details of the adhesive bonded joint and the add joints. Basically, what you see, the difference is that we produced or we prepared the aluminum in advance, and we printed the composite in advance. Then we deposit the adhesive and then cure the adhesive as following the instructions of the adhesive producer and those guidelines of the aircraft industry. And then we apply produce the AddJoining. So in this case, the alternated configuration with 0 degrees carbon fiber orientation in the carbon fiber oriented plies, and we had 8 layers in a total. Okay, these are the summarized results, where we have the ultimate lap shear force in gray, and in white the displacement at break. So how it was then, so showing the ductility or the fracture toughness of the joint. So what you can see, first of all, if we concentrate on the metal, on the ultimate lap shear force, we saw an increase of 35.3% in ultimate lap shear force, and an increase of 75% in the displacement at break, showing an improvement of mechanical resistance and ductility of the added joints in comparison to the adhesive bonded joints. And this is basically can be also better understood if you look at the tested specimens. So in dark is the adhesive here. So this is the metal side, this is the metal side, and what you see is that the failure took place between the adhesive and the 3D printed composite parts. So that led to an adhesive failure, reducing the mechanical resistance, while in the case of the added joints, the failure didn't took place in the coating layer and the first printed layer, but as we publish in other papers, this fracture takes place between the first layer of carbon reinforced composite and the unreinforced composite. So is a failure in the composite part, so a cohesive failure in the composite part. So that's explain a better mechanical performance. So with that, I can finalize this presentation, summarizing first of all that the correlations between the AddJoining process parameters and the ultimate lap shear force were analyzed and established, whereby we saw that the number of layers and the orientation of the layers, as well as the types of distribution of those layers, will influence the lap shear mechanical resistance. And in comparison to the state-of-the-art adhesive bonding, we are able to produce stronger joints with better ductility in comparison to the adhesively bonded joints, showing the potential of this technology. Before concluding this presentation, I would like to acknowledge the sponsors of my endowed professorship, which are voestalpine, Diamond Aircraft, Fuchshofer, and TCM as industry, the academic partners, the Institute of Vehicle Safety, the Engineering Production, and mainly for the Federal Ministry of the Republic of Austria and Climate Action, Environment, Energy and Mobility, Innovation and Technology, so the BMK, for the financial support, and to thank CNPq Brazil for sponsoring the scholarship of Dr. Falck. I would like to thank you for your attention. I'll be glad to try to answer your questions in case you have. Thank you.